Finding percent dissociation is pretty straightforward. You just take the amount of the substance that is formed whenever it dissociates, divide it by the initial amount of the substance. It's a percentage, so multiply it times 100, and you're there. We actually did this, if you look back at this problem here, we did this back here at this problem already, so we already know how to do this. Percent dissociation is not a set value for a certain substance. The more water that you put into this, the more dilute it becomes, the more it's going to dissociate because the more water there is, the more it comes into contact with the water, so the more it will dissociate into the water. So let's take a look at one of these problems. Alright, so taking a look at this problem, we're going to find the percent dissociation for a 0.1 molar HF solution and for a 0.01 molar HF solution. To do both of these, we want to start with our balanced chemical equation. And we're going to go ahead and set up an ICE table for this. One thing that this problem is missing that it has to have is it has to tell you a Ka value, otherwise you wouldn't be able to do this problem. So I think I must have just left it off when I typed up the notes, so I'm just going to look it up in the book. Alright, so our original amount of HF is 0.1 molar. Original amounts of H plus and F negative are 0 and 0. The change value, we don't know what it is, minus x plus x plus x. Okay, this is going to be 0.1 minus x, this is going to be x, this is going to be x. And we're going to plug this into an equilibrium expression. And if we go through and solve for x, we're going to get 7.9 times 10 to the negative third molar. And then to find our percent dissociation, we just take the amount that it dissociated into, which is this, divided by your original amount of the substance, which is 0.1 molar. Multiply that times 100 because it's a percentage. And we're going to get about 7.9%. Now, if I do this for the 0.01 molar solution, it's the exact same thing. Instead of the 0.1, I put in the 0.01. But everything else is pretty much staying exactly the same. So if I go through and do all of this, then what I will get for x, instead of 7.9 times 10 to the negative third, I'll get 6.8 times 10 to the negative fourth. Okay, divide that by your original amount, 0.01, and you're going to get 23%. Now notice that whenever we had a lower concentration, we had more percent dissociation, and that is always going to happen. Polyprotic acids are acids that have more than one ionizable hydrogen atom. Alright, so these are going to be things like H2CO3, H3PO4, pretty much anything that has multiple hydrogens that can dissociate to form hydrogen ions when you put it into water. HCl would not be polyprotic, that's monoprotic. Polyprotic acids always have what is called stepwise dissociation. That means that they tend to get rid of their hydrogens in steps instead of all at once. So for example, if you have a polyprotic acid like sulfuric acid, it doesn't dump all of its hydrogens off right away. Instead, it gets rid of one hydrogen first, and then the ion that forms as a result will then get rid of its hydrogen. Now, it's always a lot easier to remove the first hydrogen than it is to remove the second hydrogen. That's because whenever it loses its first hydrogen, it becomes an ion, and it's a lot harder to remove a positively charged particle from an ion, a negatively charged anion, than it is to remove it from a neutral substance. So that means that this first reaction, the first stepwise dissociation, is going to occur a lot further to the right than the second one. The second one is not going to occur as far to the right because it's harder for it to lose its hydrogens. As a result, the Ka value for the first reaction is going to be a lot higher than the second one is going to be. So the two Ka values are going to usually be pretty different. If they differ by a factor of at least 10 to the third power, then you can just focus on the first Ka and kind of ignore the second one, because the first one is really the only one that's producing appreciable hydrogens. The second one isn't producing enough to really matter. So let's take a look at an example of this. Here we have carbonic acid and its dissociation. Notice that the Ka value for carbonic acid for its first dissociation and second dissociation are very different. This one's a lot larger than this one, and so it's really only the first value that's important. Oh, and those weird little dots there, those are meant to be equilibrium signs. It didn't format very well on my computer for some reason. Now there's only one polyprotic acid that is strong. All of them are weak except for sulfuric acid. It's the only strong polyprotic acid. And almost all polyprotic acids, it's the K1 that's important. But in sulfuric acid, it's the K2 that you're going to be using. The reason why is because K1, its value is just so ridiculously high that we don't really even have a good value for it. And so we go ahead and use the K2 value, because even though it is a stepwise dissociation, the second dissociation is still so strong that we really can't ignore it. All right, so let's take a look at an example problem here. Dealing with a polyprotic acid. What's the pH of 0.0037 molar solution of carbonic acid? What would be the concentration of carbonate ions in the solution? So to solve this, we start out like we do with all the others, with a balanced chemical formula and an equilibrium expression. Now, since this is a weak polyprotic acid, I only deal with the first dissociation, so I do not dissociate the second hydrogen. I only do the first hydrogen. Now I can use the Kas that it gave me just above this and an ice table to figure out what the concentration of hydrogen ions is going to be in this substance. So I'm going to go ahead and start with my ice table. And I know the concentration of carbonic acid is 0.0037. And I know original concentrations of these are 0, 0. Now this is going to change by x, x, x. I get 0.0037 minus x, x, and x. And like I said, I'm going to use the value of K that I had up above and plug that into my equilibrium expression. And when I do this and I solve for x, I get 4 times 10 to the negative fifth molar. Now this is equal to my concentration of hydrogen ions, so I can use that to find pH and to get a pH of about 4.4. Now to solve the next part of the question, what would be the concentration of CO3 negative in the solution? This is where it's going to start to get a little bit tricky. I don't have CO3 negative in this equation here. I have HCO3 negative. So what I'm going to have to do is I'm going to have to take this down to my second dissociation. And here's where it gets kind of tricky. I have to go back and I have to figure out what the concentrations of these substances are in the problem, and pay real close attention to this because this is really weird. Now the HCO3 negative, if we look back up here, the HCO3 negative is going to be equal to this amount here that we got right here for X, all right, which we found was equal to 4 times 10 to the negative fifth. But when what we're used to doing is we're used to writing a 0 here and a 0 here, but there's been some hydrogens that have already been made, all right? We made hydrogens back here in this problem right over here, okay? We made 4.0 times 10 to the negative fifth hydrogens, and we can't forget those. They still have to be present. But we did not make any CO3 negative in the last problem, so we have initially 0 amount of CO3 negative. Now, since we have no CO3 negative, that means that our reaction is going to naturally move towards the right. It can't move to the left because there's no CO3 negative, so it's going to have to move over towards the right. We don't know how much it's going to move over. We just know it's going to move over by a certain amount. Okay, so we're going to lose a certain amount of X from the HCO3 negative and add a certain amount of X to the H plus and the CO3 negative. So that when we get our equilibrium values, we have 4 times 10 to the negative fifth minus X, 4 times 10 to the negative fifth plus X, and we have X. Once we have these, we can plug them into our equilibrium expression. And again, looking back at the top of the page, we can look at those values for the second dissociation of carbonic acid and use that for our value of Ka. Now when we set this up, since the value for Ka is so ridiculously small, remember that we can say 4 times 10 to the negative fifth minus X is pretty much going to be equal to 4 times 10 to the negative fifth, same thing for 4 times 10 to the negative fifth plus X. And then we can simplify this, plug this on in, and we get a value of 5.6 times 10 to the negative 11th for X, which is equal to the concentration of our carbonate ion.